Hi everybody, Dr. L here, and in this segment we are going to go through and implement logistic regression with a data set in R. We're going to do this using the code chunk that you hopefully have access to, and otherwise you can find the data set at my GitHub repository located at this URL. But we're going to go ahead and just run line number 7 to import that data set. And we'll do a little bit of exploratory analysis here using lines 10, 11, 12, and 13 to run the head function to take a look at the structure of our data set. Just a quick preliminary look here. And we can see down in the console window, okay, these first 6 observations. And note we have 4 different variables. We have an admit variable, which is binary, 0 or 1. Either the student was admitted to the graduate program or they were not, 0. We have the student's GMAT score out of 800 points. We have GPA measured on a 4-point scale for grade point average. And we also have a measurement of rank, of the rank of school, undergrad institution the student was coming from. And the rank variable has 4 levels, 1, 2, 3, and 4, with 1 being the highest tiered school, highest ranked school, and 4 being the lowest. Let's go ahead and take a look at the summary output for some of our descriptive measures for the data set here. So we free up a little bit of room down in the console window. Let's go ahead and run line 11. And we can see here, if we look at the admit variable, okay, note that the mean of this binary variable is 0.3175. And the way we can interpret that is if you were to add up all the observations, which are all 0s and 1s for that variable, 31.75% of them are 1s, meaning out of this whole sample, it looks like the admissions rate is about 32%, 31.75%. Not too much interesting things going on with the other variables. The one thing I am going to note here is that the rank variable itself, we're going to have an issue with because it is coded like it's a numerical variable. But when the number goes up by 1, it doesn't really have a numerical translation. It's actually a categorical variable. Which class of rank was your undergraduate education from? So we're going to deal with that in a moment. In fact, we're going to build a logistic regression without changing that first. We'll see what the implication is of interpreting the data and rather the output from building that model. But the dimensionality of the data here, we have 400 rows of observations. We have these 4 different variables: admit, which is binary, GMAT, which is numeric, GPA, which is numeric, and rank, which looks numeric but is actually a categorical variable. So we're going to go ahead here and we're going to build a logistic regression model treating the rank variable as a numeric variable, which is really how it's coded. But note here, it is actually a categorical variable. And we are going to do this using, instead of the LM function, we're going to use the GLM function, which is general linear model, which essentially allows for the dependent variable to be non-normal here. And the GLM function, we're going to feed it information very, very similarly. So here is our Y variable, admit. Notice it's going on the left of the tilde sign here. And we're using the dot to say we want to regress admit on all of the other variables, on GMAT, GPA, and rank, those 3 other variables. We're still feeding it the name of the data frame, but we have to feed it this extra argument. We're telling it which family of link functions to use, or transformation functions. And the binomial family is associated with the logistic transformation function. So that is how we are telling it to use the logistic regression within the GLM family. So we're going to go ahead and run line 17 to build model 1.1. And then we're going to go ahead and take a look at some of the output from model 1.1. Okay, so a few things. First off, residuals in the GLM framework with logistic regression, we refer to them as deviance residuals. And some of the standard output looks a little bit different than when you use just the regular linear model function. You'll notice most of what we're seeing here in the console window is fairly familiar with respect to our parameter estimate diagnostics, right? This table here should look really, I'm sorry about that. This table here should look really familiar. Okay, so what do we have there? Well, we have our beta values. There's our beta 0, B1, B2, B3, so on and so forth, coefficients on each of those X variables. And we can also take note here of our significance codes. We have statistically significant results at least the 5% level for all of our parameters, the intercept term, the GMAT variable, GPA, and rank. Now, you'll notice the coefficient on rank kind of has a strange interpretation. It is negative, and that actually makes sense here because if your rank number goes up by 1, okay, what is that telling us? Well, it's telling us we're actually decreasing the quality of your undergrad pedigree. Okay, and that's actually associated with a reduced probability of being admitted, which is why that negative sign is there in front of the rank variable. And that is definitely a significant effect. Now, a couple other metrics in here that are important. You'll notice there's no R squared reported. Okay, and in terms of goodness of fit, we're actually really interested in looking at something called the deviance, really the null deviance versus the residual deviance. And the null deviance is a measure of error when you only estimate the model with an intercept term and no X variables at all on the right. Okay, what happens when you add X variables in? Well, it's going to reduce that deviance. So the comparison that we're going to look at here is the value of the residual deviance down here. Okay, you'll notice that's a little bit lower. It's about 40 points lower than the null deviance. And what that means is when we include GMAT, GPA, and rank, okay, when we include those 3 variables in addition to the intercept, it improves the fit of the model by that reduction when we compare the residual deviance to the null deviance. Okay, the other important part of this output that you should notice here is that it provides us something called the Akaike information criteria. And this is useful for model selection. It's actually a way of trying to utilize the in-sample data to predict your out-of-sample generalization performance. And when we are comparing nested models, the AIC is very useful in that we generally want to look for a model that has a very low AIC score. The ones that have lower AIC scores tend to perform better out of sample in many cases. In many cases, I don't want to say in every case. And last but not least, we have the number of Fisher scoring iterations, the number of iterations it took for the algorithm to converge on the optimal parameter values. It took 4 iterations to do that, so pretty quick. So that is what the diagnostic output generally looks like when you summarize that GLM function. So let's go ahead now and take a look at dealing with this rank variable, which is originally coded numerically, right? But we said before it's actually categorical. Before we do that, I'm going to show you just very quickly how we can compute the signal S. Okay, what is the signal? The signal is really just beta transpose X. Okay, it is the sum product of the beta vector with the X features. That is what the signal is right here. Okay, so if we wanted to compute that on the training data that we used to build the model, all we're going to do is we're going to run the predict function using model 1.1 with our data frame, and we're going to store that in a variable called signal. So that's what the predict function does. That's why we didn't really have to do too much in the linear model framework, is because the linear model, the y variable was just equal to the signal. Right? We had a linear transformation function. And what we can do here is we can run the signal through the logistic function, okay, which is 1 over 1 plus e to the minus s. That was at least one algebraically equivalent form of it that we saw in an earlier segment. And what that will do here is give us a predicted probability, right? When you run the signal through the transformation function, it converts it from a negative infinity to infinity domain signal into a 0, 1 probability measure through that soft threshold. So we run line 24 and we can view what this value of predicted probabilities looks like. Here it is. These are our predictions for every single observation. So it looks like observation 1, that student we would predict will be admitted with about 19% chance. Observation 2 would be admitted with about 32% chance. Observation 3, very high admissions probability, about a 72% chance of being admitted, so on and so forth. Okay, so that is how we generate the predicted probabilities of observing the y variable. All right, another way we can generate the same results, exactly the same results, is if we feed the predict function the type equals response argument here. So if we go ahead, we feed the predict function this particular argument. Now we are essentially telling R that we want you to use that soft threshold. We want a probability response. And if you do this, and we were to run line 28, you will note that we wind up getting exactly the same set of probabilities, about 19% chance of admission for individual 1, 32% chance for individual 2, 73% chance for individual 3, so on and so forth. So these are two different ways of generating the predictions in the logistic regression framework. One was you predict the signal first, and then you run that through your transformation function. And the other one was you could just build that right in to the predict function by feeding it this type equals response argument. Now, one issue we talked about before is that rank itself was not a categorical variable. It was actually coded as a numerical variable, but it is a categorical variable. So what we can do here is we can use the as.factor function in order to convert, or really the factor function, in order to convert a variable into a factor. And I have it commented out here for the admit variable. You could transform the y variable. It actually doesn't make too much of a difference here, whether it's an integer, binary integer, or if it's a factor. But the cat rank variable we're going to create, that's a category rank. And all we're going to do is we're going to take the same information from the original rank variable, and we're going to store it in this new variable called cat rank. And now if I run the head function on the data frame, you'll notice we have a fifth variable here. And that fifth variable is cat rank. And if you look, it has exactly the same information content as rank, right? Exactly the same values for each observation, but R will treat it slightly differently when we use that variable in a model we are trying to build. For example, if we run line 34 here and we check the class of cat rank, okay, it's telling us down here that cat rank is a factor. Okay, it is a factor variable. Meaning it's a qualitative variable. Now it's not numeric. If I was to run that same function again, let's say on just the rank variable instead of cat rank. Okay, so now down on the console, we're running class on just the rank variable. You'll see that's an integer, so it's still coded as a numeric variable. So we're going to build the model with cat rank this time instead of rank. And I'll go ahead and in line 37, I will write that out explicitly. Go ahead and write that out explicitly. So we have GMAT, GPA, and cat rank instead of rank. I could have also done the dot and then minus rank variable. But let's go ahead and run model 1.2 and compare the output to model 1.1. Okay, so the first thing to note is that we have more variables showing up. In fact, what R has done now is, now that we made cat rank a factor, okay, R has created 3 dummy variables capturing whether or not our rank is tier 2, 3, or 4. And the tier 1 rank is actually built into the intercept term. Right? So the way to kind of interpret these coefficients at this point is, when we move from a tier 1 school to a tier 2 school, okay, what that does is it reduces the log of the odds ratio by 0.675. It reduces the log of the odds ratio by 0.675. If we go from a tier 1 school to a tier 3 school, that reduces the log odds ratio by 1.34. Okay, so on and so forth. So we can see here, moving to a lower ranked school, it does reduce the probability of being admitted. It's reducing that log odds ratio of being admitted. And the other thing to note here is we really use the same information content, so it shouldn't be too startling that our model is exhibiting all of these individually statistically significant results here at least the 5% level. Again, note the change in our null deviance, I think, was pretty close to about the same as what it was when we did not have cat rank coded individually as dummies, but we treated it as numeric. And the AIC is also about the same here. In fact, I think the predicted values will be about identical if we run them. Note here, our Fisher scoring iterations algorithm converged and found those optimal parameter values in 4 iterations. Okay. Note we're still getting positive effects here on the GMAT score. GMAT still is improving the log odds ratio of being admitted, and the GPA has a pretty big effect as well. So let's go ahead now and build some confidence intervals. Okay, there's actually a few different confidence interval functions in R. If you run confident on a GLM object here, it'll report the confidence intervals for your parameter estimates, but using a profiled log likelihood standard error treatment. There is the confidence intervals for the 95% level. Okay, and if you run them using the typical standard errors, using the confident.default function here, you'll get confidence intervals that are slightly tighter at the 95% level. There's a slightly smaller margin of error associated with those. So 2 different ways you can think about reporting the confidence intervals there. One uses the profile log likelihood treatment. We can also go ahead and create a confidence interval table. We've seen this before by using that cbind function with our coefficients, and we can display that table. Again, note that the way we interpret these betas, and that is what we are looking at here. These are all the different betas right here. Okay, those are showing us the partial effects of these inputs, but on the log of the odds ratio, not on the odds ratio itself. So one way we saw in the earlier segment that we could slightly improve that interpretability here was by utilizing the e base function, the exponential base, and raising e to the power of the beta. So we're going to do that. We're going to transform this whole table to the base e. And this is the same information. It's just all of the corresponding values. For example, if I took the number e and I raised it to this exponent, then what will we get? We would get this number here. Okay, now this has a little bit better interpretability in terms of the partial effects here. What that term in blue in the bottom says is that if we have a 1 unit increase in the GMAT score, okay, what that does is it increases the odds of admission, right, in terms of that odds ratio by about 0.2%. Okay, by about 0.22% or 23%. Now you'll notice GPA has a much more significant effect. If your GPA goes up by a whole point, okay, what that does is it actually increases the log odds ratio by a factor of 2.23. So by about 123, 1.23 or 123 gross increase in your likelihood of being admitted. So that factor there, 2.2345448. Okay, that says holding everything else fixed, if your GPA goes up by 1 point, that increases the odds of you getting in, the ratio of those odds, by more than a factor of 2. Okay, by more than a factor of 2. Now, how do we interpret this value here of around 1/2 for CAT rank 2? Well, remember, CAT rank 2 is the dummy variable for moving us from tier 1 to a tier 2 school. So if we were to do that holding everything else fixed, that multiplies the odds ratio by 0.5. So it actually reduces our chances of being admitted by about 50%. If you're not in a 1-tier school, but you go to a 2-tier school, that movement down the ladder of pedigree in this data set looks like it is about an effect of reducing your probability of admissions by 50%. If you go from rank 1 to rank 3, cuts that probability about in half. You're down to about a 25% chance of being admitted, 26.18% chance of what it originally was. So that's representing there about a 75% chance reduction in your likelihood of being admitted. Similarly, this value of CAT rank 4, 0.21, okay, that represents about an 80% chance reduction in your likelihood of being admitted if you were to go from a tier 1 to a tier 4 institution here. But biggest predicted effect is certainly college GPA. That is certainly a large effect there. GMAT, not so much, really close to 1. Right? If we multiply by 1, we don't change the odds ratio very much at all. But it looks like rank here is definitely telling a story. Anyhow, let's go ahead and work on some validation in the GLM framework. I'm going to use the Caret library, and I know I've looked at a lot of folks' code, and I've seen you guys use different ways of partitioning your data. There are some other creative ways of doing this. This is just one. But I'm going to go ahead and load the Caret library, and for whatever reason, folks with Macs tend to have issues loading the Caret library, so you got to look carefully down at your warning messages below. Okay, and notice I have some warnings here, but it's no errors. Okay, I got some warnings, but no errors. If you get an error message that tells you, hey, we need to install another package before you can install Caret, then follow those instructions, install it, and then try Caret again. Okay, and if you keep winding up getting some message that says you need a different package and a different package, keep installing those prerequisite packages. You will eventually get there and be able to install the Caret package. And just a refresher to install that package. Okay, you can use the command line install.package function, or you can click on the packages tab over here, hit the install button, and search for the name of the package and hit install. Okay, and we're going to go ahead and use this create data partition function. Okay, a couple arguments that I'm feeding in here to help me break up my data set into training and testing sets. Okay, first off, I'm telling it which variable is the Y variable that I'm going to be classifying through. Then I'm telling it the probability I want an observation assigned to the training data. So 70% training, the rest is going to be testing. And we're going to feed it this list equals false argument. And what that will do here is create an index of values that will track randomly. It'll randomly select 70% of the observations. And then we're going to run line 64, which says, let's pull only the observations that we've stored in the index in train. We're going to pull only those rows. So notice we don't have anything after the comma. We're taking all the columns, but we're taking only the rows in train to store in the training data. So I've now created a training data set. And we can see that training data set is over here. Contains 280 observations of those 5 variables. Remember, we added that 5th cat rank variable. And you can check fairly quickly that 280 divided by the 400 that we had is exactly 70% of the data. And this was done randomly. Okay. So again, it's important here, and I'm going to do this again just so you can see that we're setting the seed, because this step here is random. I'm going to set that seed so that way you guys can replicate the same results as me. And I'm going to run those 2 lines together. So my training data again is now randomly generated, 70% of the data, and the rest of it, what is not in train, that minus in train, so those things that are not in those rows, I'm storing in the testing data. And we can check here the dimension of the testing data. And we can see there's 120 observations with 5 variables, and 120 over 400 is exactly 30% of the data set. So we have our training partition. Boom. We have our testing partition. Boom. All right, so let's go ahead and run some prediction with logistic regression. Okay, we're going to build a model here where we're predicting admissions from the GMAT score, GPA, and the CAT rank variable, which again, we converted to a categorical variable, to a factor. This time, you'll note we are specifically here going to be using only the training data to build the model. Okay, so we'll see similar effects as we did when we built model 1.2 earlier, but it's not going to be exactly the same because we've sampled a subset of the entire data frame. So let's go ahead and build that. Note here, I'm saying we need rank to be a factor variable. If you wanted to run this regression with the rank variable instead of cat rank, but I commented that out there, so you don't really have to worry too much about the contents of this particular comment here. But let's go ahead and run line 74. We'll build the model, and then we'll take a look at the summary output of the model. So note we're getting some very similar things. Okay, we can see here our partial effects are more or less what we would expect them to be. We got negative partial effects on these cat rank variables, and those effects get bigger as the tier of school gets worse. We had a much larger effect from GPA. It was positive compared to GMAT. And it looks like in this model framework, GPA actually becomes insignificant as well as cat rank 2. And you can see in the far right here, we're only getting significant codes for the intercept, for the GMAT score, for cat rank 3, and for cat rank 4. So it looks like that cat rank 2 effect kind of went away. Maybe that's a function of the particular training data that we had pulled here because that was significant beforehand. But remember, we sacrificed some sample size as well. So that causes our standard errors to go up a little bit. Note the Ikaike information criteria here is down to 304. Okay, and we have a drop again in our null deviance when compared to the residual deviance. We lost about about 30 points. All right, so let's go ahead now that we've again looked at the diagnostic results here and go ahead and take a look at our coefficients after we create the confidence interval table and we raise them with the base E. All right, and again, we're seeing similar effects here, right? GMAT score pretty much had a very small positive effect, but it was pretty much a multiplicative factor of 1 in how it affected the odds ratio. GPA, this model says if you increase your GPA by 1 whole point, so you go from like a 3.0 to a 4.0, what that does is it increases the increases the odds ratio of being admitted by a factor of 1.66. You get about a 66% increase in your likelihood of being admitted if you get a point increase in your GPA. And that's again holding all other factors fixed. Cat rank 2, looks like we get about a 40% reduction in our likelihood of getting admitted when you go from a 1-tier school to a 2. We get about a 70% reduction in the likelihood of being admitted if you go from a 1 to a 3. And we still get about an 80% reduction in the likelihood of you being admitted if we go from a tier 1 to a tier 4. So that's all consistent with what we saw using the entire data set. Let's go ahead now, and what we're going to do is we're going to build something called a confusion matrix, which will allow us to compare the reference values in the data, 0 or 1, were they admitted or not in the data, to our actual predictions, 0 or 1. Okay, and so we're going to feed this function here, the confusion matrix. We're feeding it the table function, and we're going to make a table. And we're feeding the table function the predict function. We're giving the predictions for the MLOG model we just built from the training data. Okay, and we're telling it it's a response type, and we're feeding it another piece of information here. We're going to tell it if the probability is greater than or equal to 1/2, then we're going to be assigning it a value of 1. If your probability of admission is higher than 50%, we're going to predict that we should admit you. If it's lower than 50%, we're going to predict that we shouldn't. So this value here, it's kind of important. I want to mention this. That is a threshold. Okay, that's going to define the rate at which we would be accepting students based on this model. If we increase that threshold to, let's say, 80%, okay, then we're going to wind up admitting fewer students because we would need the probability of your admissions to be above 80% to say, yes, we're going to take you, based on our predictive model here. So this parameter 0.5, that is something that you can tweak, okay, which is going to affect your specificity and your sensitivity, the rate of false positives and false negatives in the data set, or rather in your model when you're trying to predict. Now, this is on the training data. We're going to run line 81 on the training data. Okay, and what we're going to do is we're going to look at the output provided by the confusion matrix on the training data, and then we'll go ahead and compare the same output to our test data. And when I run line 81, I'm going to give us a little bit of room down here in the console window to look at the output. There's quite a bit to look at, so let me scroll up here. So this is the output. Okay, it's showing us the confusion matrix and statistics. And you'll note here we have a confusion matrix. Okay, if you were to add up all the numbers in that matrix, you would wind up getting the 280 observations in the training data. And the values false and true actually stand for reference values of 0 and 1 in the data. 0, true is 1. We should admit you. And these values up here, these are the reference values. The columns are the actual values in the data. Okay, conversely, along the rows, okay, again, false is 0. Just move that over a little bit. False is 0. True is 1. Hey, but along the rows, what we're actually measuring are the predicted values. So use a blue arrow for that. 0, 1 here, the row is really the predicted value. So this confusion matrix, what this does is it shows us the degree to which we were actually correct. So if we look at the first column of information in the confusion matrix, what that tells us is that we had a total here of 76 individuals that were admitted in the data. I can add these two entries together. 63 plus 13 is 76. And out of those 76, our algorithm here, our model has correctly identified 13 of those individuals. Okay, so 13 out of the 76 total, you can check this calculation, but that actually comes out to about 17% specificity. That is the probability of us predicting admission correctly, given that they were actually admitted. Okay, so that is the true positive rate here, which means we have a, the complement of that probability there is about, what is it? About 83% chance that we would by mistake reject somebody that we should have accepted. You wind up getting a false negative there. So the point is, from that particular analysis of specificity, is that we're not great at figuring out who we should admit. Only about 17% specific on that. Now, what are we really good at here? I'm going to argue we're really good at figuring out who we should reject in this case. Okay, in our sample, we had 192 plus 12 folks. So we got here 104 individuals that in the data were actually rejected. And we correctly, we got 204 individuals in the data that we rejected. And we correctly reject 192 of them are correctly rejected. So 192 out of the 204, that gives us this sensitivity probability of about 94%. We're about 94% sensitive. Given that we shouldn't have admitted them, we correctly predicted that with our model 94% of the time. If you were to add up the two values circled in yellow, or in orange rather, 192 plus 13, as a fraction of the entire 280 observations, that gives us maybe the most important metric to look at here, which is our accuracy metric. Your accuracy metric says we are correctly predicting 73% of the classes in our training data set. And note that they report a confidence interval on the accuracy metric here, given that there's a little bit of noise in it. So our accuracy is really somewhere between 68 and 78%, somewhere in that range at the 95% confidence level. But what I want to just show you for a moment here is what will happen to our sensitivity and our specificity if I was to increase that threshold of 50% probability. So I want you to think about these two values. Sensitivity, I want you to remember that number, 0.9412. Specificity, 0.1711. In fact, let's maybe write those over here. Okay, so what was our problem? Well, our problem was we were really good at rejecting people, but we were not really good at accepting people. Really good at rejecting people, not really good at accepting people. So let's go ahead and change the threshold in line 85. We're going to go ahead and change this number here and look at how that affects the sensitivity and the specificity values. So before we do that, let's go ahead and clean some of this up here. Okay, I'll leave the sensitivity and specificity values that we wrote there on the right. We're going to go ahead and run line 85 again. My apologies, I meant let's run line 81 again. Let's go ahead and change this value here of 0.5. Let's bring that down a little bit. Let's not be as critical of the applicants, if you will. Okay, and let's change that down to 25%, meaning if the logistic regression model predicts that they should be admitted with a probability above 25%, we're going to go ahead and admit them. Okay. What is that going to result in? Well, that's going to probably result in more people admitted Okay, but remember, we were not good at admitting people we should have to begin with. That was why we wound up with this really low level of specificity to begin with. We were not good at admitting people we should have. So if we lower the bar a little bit, maybe we should get more of those people in, but that's going to be at the expense of us admitting some people that we shouldn't have. So we're going to probably wind up seeing here our specificity will go up, but our sensitivity will wind up going down. So let's go ahead and run line 81 again and build the same model and take a look at the sensitivity and specificity results. And I think as we predicted here, the new specificity is way higher. Given that we should have admitted them, we're correctly admitting them 71% of the time. And given that we should have rejected them, we are correctly rejecting them 60% of the time. But notice our overall accuracy has fallen. And whether or not that's important, okay, which is more important, really depends on the costs of you making false positives or false negatives. The cost of you admitting someone you shouldn't have versus the cost of you rejecting somebody that you shouldn't have. Okay. If we were to make that number higher again, if we went back to line 81 and we changed it, let's say up to 0.75, you need a 75% chance to get in now. Sorry about that. What did I do? Let's go 0.55. Okay, now we made the specificity even lower than the 17% at which we started. So we are incorrectly rejecting applicants we should have accepted about 90% of the time, but note we're really good at rejecting applicants. Now you have to be a little careful looking at sensitivity, specificity, and accuracy. Imagine in our data set, if we had 280 applicants where 270 of them were rejected, then our algorithm, okay, could decide, hey, maybe the best thing to do is just reject everybody, and we'll be right at least 70% of the time. So if your predicted value is really skewed, okay, you may have to consider tweaking that threshold and considering the balance of specificity and sensitivity over just the accuracy measure itself as kind of your key guiding light. But in general, accuracy is what we are looking for if we're not too worried about the asymmetric costs associated with false negatives and false positives. Now, back to our original results here. When we used a 0.5 threshold, oh, sorry, that was on the wrong, that was on the test data. We were looking at the training data still. So let's bring this back down to 0.5, run the confusion matrix on the training data. And this was the original values that we were getting before we had played around with that 0.5 threshold. Here was our original confusion matrix. We had about a 73% accuracy rating on that training data set with our model. And specificity was 17%. Sensitivity was 94%. So we were, again, really good at rejecting people we shouldn't have accepted, but we were really bad at accepting the right people who should have been accepted. Now, what about on the testing data? We partitioned our data. We know we are 73% accurate on the training data. So that's actually our measure here of error in the classification algorithm. We can use accuracy. We may use sensitivity or specificity depending on the application. But what do you think will happen when we run the same model on the testing data that we did not use to build the model? Well, hopefully you're thinking that our accuracy on that data should not be as good, and we can get a prediction of our out-of-sample accuracy using our testing set. So I'm going to run line 85 now, finally. I know I accidentally hit it a couple times. But when we run line 85, note here that I'm running the same model, mlog, but I'm doing it on the testing data specifically. Okay, in line 81, we were doing this, and I know it's subtle, but on the training data. And remember, if you are evaluating the performance on the training data, it's going to make it look above average accurate. It's going to make it look like you're too good. And it's not going to really give you an honest assessment of your out of sample performance here. So let's go ahead and run line 85, keeping in mind what our accuracy was in sample. Our in-sample error, if the accuracy was 73%, then our in-sample error was about 27% in terms of the accuracy metric. Does that make sense? 100% minus the 73% accuracy gives us an in-sample error of 27%. And let's go ahead and run line 85 now and wrap this up. We're going to run the same confusion matrix, but we're running the model on the testing data this time. And when we do that, when we run line 85, note our accuracy is a little bit lower. Accuracy a little bit lower here. So our out of sample error is like 40% on the test data, right? So it's a little bit more of an honest assessment of our actual out of sample performance here. And note with the confidence interval, if you look carefully, you know, the lower bound of the confidence interval says we're anywhere between a coin toss to predicting correctly up to about a 68%, 69% there. Note again, we are very bad at rejecting this, or at accepting the students we should have. We're only accepting about 14% of the students that were actually admitted in the training data set, or in the testing data set. But we're still doing pretty good out of sample in terms of rejecting students who should have been rejected according to the test data set. So I will leave you with that. Hopefully you will be able to go ahead and successfully implement GLM for a logistic regression for binary classification. If you have more than 2 classes, just a real quick note about this. Logistic regression is not the best option. Okay, there'll be some other options I'll talk about in a later segment. But if you have more than 2 classes, you can use logistic regression. But what you would need to do, let's say you have 3 classes, red, white, and blue. You would have to build 3 logistic regression equations. One for is it red or not, one for is it white or not, and one for is it blue or not. You would take a data point then in your test data, you would run it through each of those models, and you would see which model gives it the highest probability. If the red or not model gives it the highest probability, then you would predict that would go in class red. Okay, but otherwise, super useful model here for binary classification. But if you have multi-class problems, then there's ways you can essentially use a type of voting mechanism across the logistic regressions by looking at the one that gives you the highest likelihood of a particular outcome. So I will leave you there. Hope that helps, and I will see you soon.